Good.
This is the last slide of equations and then stop. Just to remind you that we are considering a full cell stack. So for example, in the project, you will have to simulate a stack. How can you do this? Well, actually, the overall voltage of the stack, since all the fuel cells are in electrical series, the overall voltage is the sum of the voltage of all the cells. Okay? But what you can do is to consider an average cell having an average voltage and then multiply the voltage of this average voltage by the number of cells and so get the overall stack voltage. This is acceptable basically, at least at the beginning of life for a car where all the cells are working very similarly. Then it could happen that some of them go through a different degradation process. So maybe during lifetime of your vehicle it could be that the difference between the average and the minimum or the maximum voltage of the cell could increase because of this. But generally, the design of the stack is done in order to have the most possible average distribution, even distribution of voltage of the cells. Okay? Okay. Instead, the stack current is much easier, being them all in electrical series. Okay? This means that the average current density, J, multiplied by the size of each cell, of one cell, will give you the whole current that is going in the stack. That is going in the first, in the second, in the third, and so on, in all the cells of your stack. So, the point is, if you break one cell, okay, it will be impossible to run your stack, okay, because this current must go through all of them, okay, so you have to check a lot the gradation of the cells, because if you break one of them, basically your car will run no more. But luckily this is something that happens very seldom. Okay, then you have the stack power, that is obviously the current by the voltage. What you get in the end, that the stack power is the overall current of the system. Oh, I forgot here in I. Let's fix it immediately. This is the J. Okay. So you have an average current density multiplying the surface of the cell, the average voltage, and the number of cells. Okay? The point is, if you want to increase the stack power, you have to increase the number of cells. Okay? So if you want to have 1 megawatt power, you have to put a lot of cells in order to increase the power. Or you can increase the size of the cells. Okay? Then you have large cells. And that's it. Instead, here you have the stack efficiency. Just to remember you that the stack efficiency is proportional to the average voltage of the single cell. So the voltage of the cell is a good proxy for basically the efficiency of your stack. The higher the voltage, the higher the efficiency. Instead, the power will be mostly correlated with the current density. Okay? The higher the current you can draw, the higher the power you can get from your stack. Here you have a picture of a very old stack. Instead, here you have the stack that is in the Toyota Mirai, just to show you the difference. Okay, now let's move now to cars. In this talk now, I will show the schematic, basically, of all the components of a hydrogen fuel cell car, and basically how it works. There are also some measurements done at the Ardonne lab that show how the hybridization of this car is occurring while they're running. Now here you have, for example, the Honda Clarity. This is a picture I took in Lucerne at the conference. You have in this hydrogen car, you have the high voltage battery that is under the driver's seat. You have 2 hydrogen tanks that are in the back of the car, and then there is the fuel cell powertrain that is under the hood. And this powertrain, so the stack basically is all over there. and substantially you have here hydrogen entering your stack that is placed under this cover, and you have the air inlet that is taken from here, then the compressor is down the hood. And so you see that the problem of fuel cell cars is to make this thing very compact, because you have limitations in volume and obviously also in weight. So to have an effective powertrain of this size, that is around 100-120 kilowatt, I don't remember exactly, but in this range, you see that you have really to use all the available space and try to reduce the volume of all the components. So for automotive, volume matters, size matters, okay? The typical scheme of a hydrogen car at the state of the art is for sure made of several components. So we do not have just a fuel cell stack, that is the thing here in the middle, okay? Because you have to think both hydrogen and air, okay? So if you look, for example, at air, you're taking air from the front of the vehicle, entering into a filter, because you have to remove particulate and all the dust. It goes to a compressor, for two reasons. First, because you have to flow air into the stack, but also because you want to have the option to pressurize the stack. So to have a high power, because as we saw before, increasing the pressure of the stack, you're increasing also the power. Since after the compression, as you do know, air is generally quite hot, you have to cool it down with a pre-cooler. Then after the pre-cooler, the air is entering to a component that is called the humidifier. The humidifier has a key role because in hydrogen fuel cells you generally cannot feed dry air. You have to feed air with a little humidification at least, because dry air will cause a severe dehydration of the polymer and your cell will be unstable during operation. In order to do this, obviously, you do not have the space in the car to put a liquid water tank. No? It could be an option to have a liquid water tank, to have air bubbling through this tank, and then having kind of dew points of this air. Instead, what you have to do is to collect the water that is produced because of the reaction, and here you have basically a mass exchanger. A mass exchanger that takes as inlet the dry air out of the compressor, and it has the effect of humidifying the dry air by mass exchange with the air exiting the stack. Because at the outlet of the stack you have consumed oxygen, but you have also produced a lot of water. So at the out of the stack you have a very high humidity flow rate of air, depleted air basically. So the idea is to have a humidifier which goal is to have a counter flow exchange of dry air and humid air basically, and so you have a little humidification of air at the inlet of the stack. It's clear? Okay, this component obviously is quite crucial, and you do not have any control on this. Okay, you cannot change the voltage of the humidifier. That's the only thing you can have is to balance all the mass flows in order to avoid, during the dynamics of operation, for example, too much humidification of the air or too little humidification of the air. Okay, so it's a quite critical component in the dynamic operation that you have in fuel cell cars. Yes.
Professor, what would be the temperature of the air when it is after it is pre-cooled?
After the pre-cooler will be less than 100 degrees C, generally. 60, 80, depends for sure on the operating condition. The point is that you want to avoid to have too high temperature, which could damage this membrane humidifier.
And under what conditions can this fuel cells be operated? Like for different regions there are different air temperatures, right?
Yes.
So I'm asking what are the temperature conditions under which we can use this type of system?
Well, the point is that what you have to do basically, you can use this system. Consider that what you have to avoid is to have the fuel cell stack going at too high temperature, okay? Because we said polymer fuel cell cannot operate above boiling point of water generally. So we try to keep the stack far below 100 degrees C, okay? And that's the key point. And so you're cooling down your stack with a coolant loop. In front of the car there is a radiator. This radiator with a fan is basically cooling down a liquid, which could be oil-based or some synthetic liquid. Basically that is fed into the stack. There are some channels for the coolant. And with this approach, you are trying to keep the temperature of the stack as low as possible, around 80, 90 degrees C. So basically, the humidifier, the key point is that what you have to avoid is to have liquid water at the end of the humidifier, because entering the stack will give you too much. There will be liquid water, so it will flood all the channels and will be a problem for the operation. So the temperature of the humidifier must be high enough to avoid the liquid condensation at the outlet. The other point, it cannot be too much high, because you don't want air entering the stack being too hot, and also because it's made of some plastic materials which cannot work much higher than 100 degrees C. That's the point. Okay, so these questions help you to understand that there is a critical management of temperature within fuel cells, so that there is a high temperature coolant loop that is necessary to keep the temperature of the stack as low as possible, and also to cool down both the electrical motor and the compressor driver and all this the cooler of the air. Then the other side is the hydrogen part. The hydrogen is taken from a compressed tank. There are some safety valves, some filters. And the important thing in automotive operation is that hydrogen is fed to the stack, but then is not vented to the atmosphere. Instead, there is a recirculation of hydrogen at the anode side. So the hydrogen exiting the stack is then pumped back into the inlet, generating a recirculation of hydrogen within the stack. The recirculation at the state of the art is generally done with ejectors. Okay, so there are several ejectors, in this case one high flow and one low flow, that you can use whether you have to feed a low flow into your stack or a high flow inside of your stack. But the advantage of hydrogen recirculation are basically two. The first one is that you're not wasting hydrogen, okay? So it's a fuel. In case you decided to vent hydrogen, you are wasting your fuel, okay? That's the key point. So by recirculating hydrogen, you are increasing the efficiency of your stack. And the second point is that hydrogen at the outlet has a relative humidity that is quite high, okay? You're getting out of the stack not just hydrogen, but also water. So recirculating hydrogen, you're also recirculating water. And this is helping at the anode side, because you do not want to feed dry hydrogen, which could cause, as well as air, dehydration of the membrane. Okay? In the end, recirculation has two positive effects. You do not waste hydrogen, and you can feed a humidified hydrogen without including any humidifier, just because water that is exiting is then put back at the inlet and so on. Then, in real system, you also have to consider that the membrane, the polymer membrane, has a limited permeability, which means that oxygen and nitrogen can diffuse to the membrane and go on the anode side. Obviously, when oxygen goes at the anode side, oxygen and nitrogen react immediately on platinum and produce water, so oxygen will basically be converted into water. But instead, nitrogen will continue to be recirculate within at the anode side. So nitrogen crossing the membrane goes at the anode side, and if you continue to recirculate, at the end you will get a very high content of nitrogen at the anode side. In order to do so, sometimes in the car you have a so-called purge valve opening. So every I don't know, 20 minutes, 10 minutes, depending on the operating condition, in the car you will waste a little bit of hydrogen in order to account for, to remove the nitrogen that is diluting hydrogen at the anode side. Okay? So that's why the utilization factor of hydrogen is not 1 in the car. Okay, you're not using 100% of the hydrogen that you have in your tank, because part of it you have to waste it in this purge valve because of nitrogen crossover. Okay. So in the end, air and hydrogen mix. Actually, this is giving you obviously a mixture of air and hydrogen, so there is a safety sensor on the car that stops basically the vehicle if they detect a possibility of explosion, being hydrogen too much, not enough diluted with air in the exhaust gases. Okay, so there are also some for sure safety considerations. Is this clear? Any question? Okay. Now, I will show you a different approach. This is the Toyota Mirai. As you do know, Toyota is working on hydrogen fuel cells since the 90s, so probably they are the most experienced automotive producer regarding fuel cells. And in 2015, they released the Toyota Mirai for almost commercial level. So it means that if you are a selected customer in California or in Hawaii, you can buy a Toyota Mirai. Now, this is how the car looks like. This was at the conference in Rome. This is what you see under the hood. And this is where all the same components are distributed in a Toyota Mirai. You see here, for example, that differently from the Honda, the fuel cell stack is under the driver's seat. So it's in the center of the vehicle, keeping the center of gravity of the vehicle so quite low, which gives some advantages from the vehicle point of view. Instead, under the hood, you just have the power control unit, which means the electrical drive engine, the compressor, and so all the electrical parts. The batteries is in the back of the vehicle, and you have two hydrogen tanks, a bigger one and a smaller one, that are always in the back of the vehicle. Okay, that is probably the most protected regions in case of any crash. So this kind of fuel cell car has 370 cells in the stack. So just to give you some number, has a peak power of 114 kilowatt, and has some typical values of volumetric power density of 3 kilowatt per liter, which is high compared to diesel, low compared to diesel engines for sure. And 2 kilowatt per kilogram, that is a mass target, typical values for a fuel cell stack in automotive operation. Okay? Okay. Now, so this is how things are distributed within the car. Under the hood, as we said, there is the power electronic that is managing both the battery and the stack, because this type of vehicle is similar to a hybrid vehicle, and you have the fuel cell and the battery that are working together, and the system has to manage which one will draw the power in every situation that the car is facing. That's what we will see next. You have some electric motors down in the system, the fuel cell stack, the battery pack, as probably you know from Toyota, that they did not use in the past lithium-ion batteries, but they prefer to use nickel metal hydrate batteries. They are moving now to lithium-ions. Then there are the two hydrogen tanks and so on. Now, let's get now from this. We have also some numbers, some experiments performed at the Argonne National Lab that give you an indication on how this fuel cell car is working in the real world. And that's what we will see now. But first, let me show you what are some improvements that have been added in the Toyota Mirai compared to the state of the art. Sorry if the quality of the image is not good enough. So, here you have for sure the fuel cell stack. Okay, if we look as we did before at the air entering the system, we have basically a compressor, we have an intercooler, which means that we are cooling down the air as done before. But what is different from before is that we do not have the humidifier. They could eliminate this component. So they are feeding directly dry air into the fuel cell stack. then the air is getting out and eliminated without any specific problem. And the key point is that by eliminating the humidifier, first of all, you are reducing the volume of the powertrain because you have one component less. Okay. But second, all the dynamics of the system is much faster because the air exits the compressor and the intercooler then enters directly into the stack, and you do not have any delay because of the air entering into the humidifier. Then you have the hydrogen side that is quite similar to the one that we discussed for the Honda Clarity, but for the fact that the hydrogen recirculation is not done with an ejector, with ejectors, but instead there is an hydrogen pump, which means substantially a scroll pump. You can imagine something similar to a small compressor that is just recirculating hydrogen inside of your system. Differently from the ejector, this component requires power, so you must have electrical work given to this pump in order to have hydrogen recirculation, but you have the capability to control how much flow you are recirculating. Okay? So you have 1 degree of freedom in the control strategy of the stack. You can decide to increase the recirculation, decrease the recirculation based on what you need or the operation of your stack. Finally, you have the cooling system that is quite similar to the one observed before. There is a main radiator, then we will see something more later on. Any question? No? Okay. Now, how is it possible that they could operate the fuel cell without any membrane humidifier? So by feeding directly dry air. In fact, here you have a comparison of the old school, so you have a humidifier, as we said before, you have a dry air from the compressor that gets humidified thanks to the outlet, the air getting up from the outlet of the stack, then you have this mass exchange and you're feeding air with a relative humidity, I don't know, 20-30% at the inlet of the stack. Well, the key point is that if you operate your fuel cell in counterflow, okay, so it means that hydrogen is entering on one side of your cell, while air is entering on the other one, okay, you will basically have a region at the hydrogen inlet where hydrogen could be a little dry, but air will be very humidified. Instead, the other part of the stack, at the air inlet, it is true that air is completely dry, but on the other side, the hydrogen feed is very humidified, because at the end of the stack you have consumed all the hydrogen and you have a lot of water at the outlet. So the first point was, by operating the cell in counterflow, they could improve a lot the water management, because of having dry air, where hydrogen is very humidified, on the other side, and dry hydrogen, where air instead there's a lot of water in it, okay? Then, the other key point was to decrease significantly the thickness of the membrane, because as we saw in our previous lecture, when you decrease the thickness of the membrane, what is dominating in water transport is the diffusion of water, and instead the electrosmotic drag becomes less important. So, when you reduce significantly the thickness of the membrane, basically you can better manage the water, having a more uniform water content across your membrane. Thus, the combination of these two facts were very important. Okay? And the third one, that I have no time to discuss now, was the design of the flow field. Because you saw in your first lecture on fuel cells, that the flow fields, so the gases, are distributed over the whole surface by means of channels, some channels that are carved on the bipolar plate. Okay. Now they could imagine a different approach of the flow field, which basically air is going from down up, and liquid water, because of gravity, is going in the other sense. So in this way, inside of the stack, air that is going upward receive water, that is liquid water, that is going down in specific channels inside the stack. So thanks to the flow field design a thin membrane and the counterflow operation, they could successfully have a fuel cell working with dry air. Okay? The key point here, I think, is that basically all the concepts that you have acquired in the last lecture combine all together to show how a real car is operated. No? Now, here some results collected at the Ardone National Lab on a Mirai car running on the roads. You know, when they have this specific test for cars that are not moving around the streets, they're just in the lab, they're forcing the speed of the car, basically, and in this way they could measure the voltage of the fuel cell stack as a function of current. Okay, and this is what we called so far the polarization curve, isn't it? Okay, so this is the polarization curve of the Mirai. But the first thing to notice is that for a real car running, for sure the operation is not in steady state. Okay? So our polarization curve looks a bit scattered because actually it is not in a true steady state. There are a lot of measurements of the dynamic operation of the fuel cells. So there is a kind of scatter of the results. You also have red circles that are actually steady state values. You can check them. Now, differently also from what we saw before, is that this thing does not look much like a polarization curve, isn't it? Because what we are used to is something that looks like this, okay? Isn't it? Okay? Something like this. Okay, and that's not the case. First of all, here you have the cell voltage. The operation above 0.85 volt is totally hindered, so the stack will never work above this high potential. This is occurring because, as you saw on Monday, above 0.85 all degradation mechanisms are enhanced. So if you avoid to operate the stack above this voltage, you are significantly increasing the durability of your vehicle. In order to do this, for sure, you have always to have some power drawn from your stack that will be used for the auxiliaries and so on. Okay. Then, the other crucial point is that the limiting current does not appear. Instead, the polarization curve looks quite flat. And this is something that you can understand if you look at the next slide. Okay, so in this slide, a different fuel cell stack output, or I mean current densities, for example, you see some relevant properties. One of them is the mass flow rate of the reactants that you are feeding inside your car. You have the mass flow rate of air, that is this green thing. You see, I try to evidence it. You see that the mass flow rate of air is basically increasing when you're increasing the power of your stack. Okay? That makes sense because they are operating this car at constant stoichiometry. Okay? So when you increase the power, you're increasing the current density, you need more air, and so you increase linearly, basically, the air you're feeding in your system proportionally to the currents that you're drawing. Now, if you calculate the stoichiometry from these numbers, you find that they use a stoichiometry at the cathode side of 1.5. Okay. Similarly, you get something very similar for the hydrogen flow. The hydrogen flow rate, that is this red thing here, you see that it is as well increasing linearly during operation. So for sure you are consuming hydrogen, you feed more hydrogen, and if you calculate the stoichiometry here, you should get a value around 1. So basically they are feeding just the hydrogen they are consuming because of the recirculation. Okay? And that's something quite easy to understand. Instead, what is interesting to check is how the operating pressure is changing under operation. So let's check, for example, the air pressure, that are the green circles, that is going like this. I evidence it because maybe it is not easy to see. The idea is that in this car, at low power or low current density, the operation is done at zero gauge pressure, which means at atmospheric pressure. You know the difference between absolute and gauge pressure. Okay, zero gauge pressure means absolute atmospheric pressure. So at low power, the stack is run at atmospheric pressure. Instead, when more power is required, the pressure of the stack is increased linearly. Okay. The positive effect of this is that in this region where you could approach the limiting current, so you are compensating limitation of oxygen transport in your cell by increasing the pressure. And that's why they could get a flash polarization curve that actually, here is the voltage in red, actually this is not a true polarization curve according to our concept, because it is not performed at constant pressure, but instead the pressure is increased as far as you increase the power. Okay? That's the trick how they could get a flat voltage change with power density increasing. Okay? Okay. Obviously, as we said before, if you pressurize the air, you also have to pressurize the hydrogen. So if you look at hydrogen pressure, that is this thing here, basically you will see a trend like this, or maybe slightly lower. So basically at high power, the pressure of the anode and the cathode becomes identical. Instead, at low power, the hydrogen gas is kept always at a pressure slightly higher compared to the air. This happens because of two reasons. The first one is that hydrogen in the tank is at very high pressure, so you're not paying anything to keep a slightly higher pressure of hydrogen, okay? So you do not have a hydrogen compressor, you have in the tank, you have hydrogen 700 bars, so you don't care for this pressure to have a slightly higher pressure. You do not pay it energetically. Instead, but also, keeping hydrogen pressure slightly higher is positive because the ideal potential, isn't it? The thermodynamics gives you an ideal potential of hydrogen that increases when the activity of hydrogen increases. So you have some thermodynamical advantages, obviously, by keeping the hydrogen pressure slightly higher. You gain 10, 20 millivolts, but you can imagine that in 270 cells can be something that we do not want to waste. Okay? Obviously, you have to avoid a pressure difference between the two sides of the cells that is too high. Okay. Then here you have the efficiency of the fuel cell card. You have the efficiency of the stack, that is the purple line, and instead you have the efficiency of the system, that is the red line. Between them, the power of the auxiliaries can explain the difference between them. Okay? And as you saw before, the stack obviously at low power is not run in an efficient way, basically, so it is not run at all, so basically there should be no point at low power because the stack, or it is stopped, or it is idle at 0.85 volts, okay? You have a peak in efficiency around the minimum current that you can draw in your system, that is around 65% of stack efficiency. Then you see that the difference between the system and the stack performance becomes much higher, high current density, and this is actually because the fact that we are increasing the pressure of the air when we are increasing the power. So the compressor at high power is demanding a large amount of power, thus giving a very significant difference between the stack efficiency and the system efficiency, differently from what you could expect in case you had a constant pressure operation on your stack. Okay? Okay. Then you see that the efficiency arrives around 50% of the system. and there is a peak efficiency around 65%. Okay, that's it. Okay, this slide could look quite messy actually. I think it's important to give you an idea about the fact that a car is never in a steady state condition. So in a fuel cell car, the operating condition is extremely dynamic. Okay, in the lab we are studying all controlled conditions with constant temperature, constant current, constant voltage, constant whatever. Instead, in real world, you see that you will see now that there are a lot of dynamics and continuous changes of the performance. Now, first of all, here the car is running in a lab, and the gray line is the speed that the driver is forcing the car to go. I will keep it with gray. Basically, you see that starting from 0 speed, the driver accelerates up to 30 miles per hour. What happens in this case is that at the beginning of our test, the fuel cell stack was off. I mean, it was not required to draw any power, the car was stopped, the fuel cell was producing 0 power. Then here you have the share between the battery and the fuel cell stack when the vehicle is launched. I'll zoom a little bit. What you have in here, in green, is the power provided by the battery, and you see that as soon as you start your vehicle, the power is provided completely by the battery. Okay, that is accounting for 100% of the power that is requested during the acceleration of the vehicle. And in the meanwhile, the fuel cell stack goes through startup. So it is feeding hydrogen and air. This will take a few seconds, and then it starts immediately to draw power, which happens after the startup. And you see that almost immediately the fuel cell stack, that is which power is given by the red cube, basically is giving you all the power that you need, and the battery power goes back to 0. And this is actually following the dynamics of the load as required by the driver. Okay? And the interesting thing is that you have this continuous change of power, giving the idea of an extremely dynamic situation. Okay, so the stack is continuously changing the airflow rate, the hydrogen flow rate, in order to follow the power request of the driver. And the scale here is, I don't know, a few minutes. Okay, this thing is going on, probably less. 10 seconds, I don't know, 1 minute, something like this. Then you reach a certain cruise velocity, and you see that the operation becomes slightly more stable, being the fuel cell providing most of the power that is required, while instead the battery is charged. You see the green curve here. So basically, in fuel cells that are electrical vehicles with a very small battery, it means that this part where the vehicle is working as purely electric cannot last a very long time. Okay? The capacity of the battery, that's something you will study in the next lecture, but you can imagine it, is not able to go on providing power for hours, not just for a few seconds, after which you need to recharge your batteries. What you also see here is that when the speed is decreased, so you have a brake, in this case the fuel cell power goes to 0. And instead, the power of the brake is recovered by regenerative braking, so the batteries charges in order to recover the power during the brake. Okay? So the test goes on, there is another acceleration. You see that in between there is a stop time where the fuel cell stack is off, so there is no power required. Then the driver starts back, and again the battery giving power immediately as it is required, then the fuel cell stack providing most of the power. And you still see a condition where the speed is still limited, where there is always a share between the battery and the fuel cell stack. So, as long as you require only a few kilowatt, the battery in this kind of vehicle can still give a contribution. Instead, if you perform a test at very high speed, that is the case. For example, here you have repeated accelerations up to 80 miles per hour. So going to high speed. Here the speed is increasing a lot. It's increasing a lot in short time, then it is decreasing and increasing again, and so on. Okay, this is the speed of the vehicle. What you see in here, always the green power is the power provided by the battery, the red power is the power instead provided by the fuel cell. What you see here that during the first acceleration the battery can give still a contribution. But the charge accumulated inside the battery is soon depleted, and in the next step there is not enough time to charge back the battery. So during the next startup, actually, the contribution of the battery decreases until it basically vanishes. You see that in this kind of vehicle, at high power, the power is basically provided only by the fuel cell stack. Okay, in this case, giving you a peak of 110 kilowatt, and during this operation, giving an average stack power of around 100 kilowatt, while the contribution of the battery basically vanishes because of the low size of this battery on a hydrogen vehicle. Okay, something similar that you would expect from a hybrid vehicle, for example. Okay, but so actually, if we go back to our system efficiency, so we know that our system can operate from 0 up to 100 kilowatt. Okay, but the key point is that about 90% of the operation of the fuel cell stack is far below 20 kilowatt. So also in the design of the fuel cell stack, you have to consider that most of the time your car will operate in this region, and only during transient, so only during very extreme acceleration and so on, it will work at high power densities. Okay, and this is a very important concept, because it means that the efficiency of your system in a driving cycle or in average will be considerably much similar to the one you have in this region. Okay, so you have, thanks to this operation at low power density, you have an improvement in the efficiency of the vehicle. Now, the last concept is about thermal management, because we are energy engineering, so we care for energy. In this case, you have the fuel cell system that at high power densities must reject a huge amount of heat, okay, because of the thermodynamics and because of the kinetics and the losses that you have in your system. This heat must be removed by the coolant that is entering your system, getting out of your system, then entering in a radiator that is in the front of the vehicle. The liquid is cooled and then fed back to the fuel cell. For sure, in an ideal vehicle, you could have an infinite surface radiator, which means that you could cool down your liquid back to 40 degrees heat, ambient temperature at least, no? But in real case, instead, the size of the radiator is limited. So, it means that if you go at high power, that is done in this extreme experiment, where they are going up a 25% grade, so a very steep slope, at high power, so pedal in horizontal position, okay, starting from a room temperature condition, vehicle off, and so on. What you see in this case is that the velocity, the speed of the vehicle is firstly increasing, then going down to a level of about 30 miles per hour. And in this case, you see that the power of the fuel cell goes very fast to maximum value and then starts to decrease. And instead, to understand this effect, you check that the temperature of the stack at the same time is increasing. This is the temperature of the stack. You see that it is vastly increasing up to about 70 degrees C. And this temperature is actually measured at the inlet of the fuel cell system. So, where the coolant enters, the temperature of the stack is about 75 degrees C. Okay? But then this liquid temperature increases, and at the outlet of the stack, you have instead a higher temperature. That is the one reported here in blue. And what is critical in fuel cells is trying to keep the temperature of the system as low as possible in order to avoid this temperature going very high, okay, and consequently damaging the stack. As you saw for sure on Monday, temperature is the most parameter that is most affecting degradation of all degradation mechanisms. If you increase the temperature, you increase the degradation always, for whatever reason. So it could be also that this peak power is also managed by the system itself in order to maintain the temperature not too high. So the car itself is reducing the power that it can provide in order to avoid the coolant temperature to go too high. Okay? Still being without a range that for sure the Toyota manufacturer has decided that is enough for this kind of car when going to such a high flow. Okay? This for sure is very critical when the ambient temperature is very high. For example, in a desert, and if you're not much lucky and you have a mountain in the desert, okay, for sure this problem will be even extreme, because the radiator will have problems in cooling down the fuel cell car, and because of the low temperature operation of these kind of systems, there is a lot of work also for energy engineers regarding the temperature management of the stack. Okay, with this, I think I'm done. If you have any questions, please come. I wish you the best for the rest of the course, and whatever you may need, please write me an email or ask me. Bye.